Coulomb's law obeys an inverse square law. Coulomb's law is a specific case of Gauss's law, as we saw in an earlier lecture. And then there's the law of universal gravitation, which also obeys an inverse square law. Is there a Gauss's law, if you will, for gravity? Yes, there is. Let's go ahead and present it in the case of an example. Go ahead and write down this example into your notes. Write an expression for Gauss's law for gravity. Use the expression to calculate the gravitational field both inside and outside of the Earth. Assume that the Earth's density is uniform. The easiest way to arrive at this solution is to first of all just draw out what the gravity field looks like if you are, say, outside of the Earth. Okay, so here's the Earth, like so. Okay, the Earth has a radius capital R associated with it. It has a total mass m sub e, and the density is uniform. And then, as we've already seen in my qualitative lecture on the gravitational field lines are radially inwards towards the center of the Earth. That is, like so. And we just draw a couple of field lines like this. Like so. And now let's make a comparison between what we're trying to do here for gravity with what we already know, for example, from, say, Gauss's law for electric fields. Okay, so if we go to Gauss's law for electric fields, E dot dA is equal to Q enclosed over epsilon naught. And then for a spherical distribution of charge, of total charge capital Q and radius capital R in a previous example, we found in that case that the spherical distribution of charge behaves like a point charge. So from an earlier example, E was equal to Q over 4 pi epsilon naught little r squared. Now, we already know, of course, that the law of universal gravitation obeys an inverse square law, so then therefore we should be able to come up with an equivalent expression now for the G field, the gravitational field that is, and then therefore from that, write Gauss's law for gravity. Okay, now let's just immediately start to arrive at the answer. The easiest way to solve this problem is just write down the answer. Here's what I mean by that. Okay, when we're outside of the Earth, the gravitational field just obeys the inverse square law, where we have the constants, 1 over 4 pi epsilon naught now, replaced by capital G. The capital Q for the spherical distribution of charge earlier is now the total mass of the Earth, m sub e, and then divided by r squared. So in other words, what we're automatically assuming is that right here is a spherical Gaussian surface like so of radius little r, and then the magnitude of the G field at all points on the surface of that sphere is described by this expression. Okay, so now let's kind of work backwards. In terms of working backwards and going from here to here, we basically did the following. We did E times 4 pi r squared equals the Q enclosed over epsilon naught. This right here, of course, was then our flux integral. This right here was the Q enclosed over epsilon naught. Let's kind of do the same thing here. So I'm going to take the r squared and move it up here to the other side of the expression. But when I do, I'm going to multiply it by a 4 pi on both sides of the expression like so. Like this. Okay, and now let's go ahead and replace this right here with a flux integral. But with the flux integral, we have to include a negative sign. Like so. The reason for this is because the gravitational field on my top diagram is inwards towards the center of the Earth. So on the top diagram, right here in green, is the G field pointing inwards towards the center of the Earth. Right here at this location, for example, here's our area vector dA, like so. Notice that they are pointing in opposite directions. So then therefore, if we calculated the flux integral, we would end up with a negative number. We need to cancel out that negative sign in order to come up with an expression for the magnitude of the G field. Hence, the negative sign that appears right here. And then on the right-hand side of the expression, replacing the 1 over epsilon naught as the constant is, in this case, a 4 pi capital G. Like so. And then replacing the total mass of the Earth now, I'm just going to write this as the mass enclosed. More times than not, by the way, when writing Gauss's law of gravity, you'll use the negative sign here on the other side of the expression. That's most of the time how it's written in various textbooks. That is like so. So now let's go ahead and use Gauss's law for gravity to calculate the G field outside of the Earth and inside the Earth. Well, we actually already calculated it outside of the Earth, of course, and that's just simply this expression right here. We use that expression to arrive in general at Gauss's law for gravity. But now let's go inside the Earth. When I go inside the Earth, this is a calculation that is much the same as the spherical distribution of charge that we saw in an earlier example when we went inside of the sphere. Let me go ahead and set it up from scratch. Okay, so let's go ahead here and rewrite the problem in the following way. Okay, so now Gauss's law for gravity with the negative sign looks like this, where this is the mass enclosed now within our Gaussian surface. Okay, here's the Earth like so, total mass m sub e, radius capital R, and now I set up a spherical Gaussian surface like so inside of the Earth, where the radius of that sphere is little r. So let's go ahead now and do the flux integral. Once again, we do have to have a negative sign that appears in the calculation. So negative g times 4 pi little r squared equals then the right-hand side of the expression like so. And then what we have to do is we have to get the mass enclosed. This is where the density comes into play. We're assuming that the Earth is of uniform density, so then therefore we can think of the density in the following way. We can think of it as total mass of the Earth over total volume, like so. This is equal then to, within my Gaussian surface, the mass enclosed divided by the volume of that Gaussian surface, like so. And then the 4/3 pi's, they cancel out here and here. Okay, cross multiply the little r cubed to the other side to get the mass enclosed. So, and then it's this quantity here, which then fits into the right-hand side of the expression. All right, so let's go ahead and cancel out the negative signs. Let's go ahead and cancel out the 4 pi's, like so. And now I've got G is equal to capital G times the mass enclosed, which is this expression, like so. And then we'll go ahead and divide the r squared then to the denominator on the other side. Okay, a little r squared cancels here and here. And then therefore you end up with a G field inside of the Earth, which increases linearly. So the magnitude of the G field inside the Earth looks like this. So at the center of the Earth, for example, when little r is equal to 0, the gravitational field is equal to 0, and then it increases linearly as you move towards the surface. When you arrive at the surface, set small r equal to capital R, and then you get GME over capital R squared as the magnitude of the G field at the surface of the Earth. And then afterwards, it decreases in accordance with the inverse square law. So the graph associated with the G field here is much the same as it is for the electric field associated with the spherical distribution of charge. So if we were asked to graph out the G field as a function of small r, it would basically look like this. So right here at this point, this is the surface of the Earth. So the magnitude of the G field at that point is as follows, and then it decreases as a 1 over r squared relationship. So the magnitude of the gravitational field associated with the Earth is at its greatest value right here at the surface. If you go down into the Earth's interior, it then decreases as you get closer and closer to the center of the Earth. You move away from the Earth, and it decreases as a 1 over r squared relationship.